Hello students, hope you're doing well. In this video, we'll look at the remaining topics under rotational motion, and those topics are angular momentum. We'll see what is angular momentum, we'll try to define it. Then angular momentum of bodies which are in linear motion, angular momentum of bodies which are in rotating motion, and finally conservation of angular momentum. Now let's try to understand what is angular momentum. Moment of linear momentum of a body about a point is the angular momentum of body about that point. So like moment, what is moment? Moment is the product of quantity with distance. Now we know that moment of force is torque. Similarly, moment of charge is dipole moment. Moment of magnetic pole strength is what? Magnetic dipole moment. So in this way, moment is product of the quantity and the distance. Now for a rotating body, this angular momentum is also defined as the product of moment of inertia and angular velocity of the body. So let's try to understand how do we find angular momentum of bodies which are under linear motion, or do bodies which are under linear motion have angular momentum or do not have angular momentum, and similarly, how do we find angular momentum of bodies which are under rotational motion. Now let's first look at how do we find angular momentum of bodies which are having linear motion. So before getting into linear motion, let me consider a body moving in a circular motion as shown in the figure. Now at any point, the velocity of the body is tangential. So at that small point of time, I can assume that the body is in linear motion. And what is the momentum of the body? Momentum of the body is P. Now because angular momentum is moment of momentum, I can write L equal to R cross P. Right. So because it's a cross product, it's again an axial vector. That is, it is acting along the axis of rotation. So otherwise, what I can write? I can write L. Angular momentum is denoted by L. L equal to, I can write R cross M. Right. Where, or I can write it as M into R cross V, because R and V are vector quantities and M is scalar quantities. So now let's try to generalize the same thing, what we have done for a body which is under linear motion. Let me assume that a body is moving along a straight line, something like this. The mass of the body is M, velocity of the body is V. And I'm observing from a point P, which is at a distance of, let's say, L from the line of velocity of the object. Now I want to find angular momentum of this body with respect to this point. So let's say at any point, any given time, the object is here. I connect both of them. I'll say this is R. Now if this is theta, then what is the perpendicular length? L. Then I can say angular momentum equal to how much? I can write R cross P, which is equal to R sine theta into P. This is R cross C, which is equal to R sine theta into P. Now R sine theta, you can see it is L. So I can write this to be equal to L into P. So what is the angular momentum of this body? It is L into P, where L is the distance, perpendicular distance between the point and the line of velocity, and P is the momentum of the body. So in this way, we can find angular momentum of bodies which are having linear motion. Now what is the condition under which a body under linear motion will not have angular momentum? That is, if theta is 0. If theta is 0, then I can say angular momentum is 0. If theta is 0, the point P will be on the line. So I can say that if the point of observation is on the line of motion, then what will happen? Then angular momentum about that point would be 0. Like if you're finding angular momentum of a train moving on a track, if you're standing beside the track, the angular momentum will not be 0. But if you're standing on the track, then the angular momentum of train would be 0, because you are on the line of motion of the train. I hope you could understand that. Now this is about angular momentum of bodies having linear motion. Now let's look at angular momentum of bodies which are having angular motion. So because we know angular momentum is rotational analog of momentum, so whatever momentum does in linear motion, the same function is done by angular momentum in angular motion. So here we know that normal momentum P equal to what? M into V. So angular momentum M is what is equivalent to mass in rotational motion? It is moment of inertia. What is equivalent to velocity in rotational motion? It is angular velocity. So I have L equal to I omega. This is what is angular momentum given by for bodies which are under rotation. Now how do I find angular momentum, direction of angular momentum? In case of linear motion, how do we find? We just find the cross product and we know our right hand rule. Because it is R cross P, turn your four fingers from R to P, then the direction of thumb shows the direction of angular momentum. But in case of rotating motion, what we do is we curl our right hand four fingers in the direction of the angular velocity. Sorry, in the direction of motion of the object, that is direction of rotation of the object. Then the thumb is along the direction of angular velocity. Here you can see that the direction of rotation is like this. This is how the direction of rotation is. So we have curled our fingers in this direction, then the thumb shows the direction of angular velocity. So angular velocity and hence angular momentum. So angular momentum is an axial vector which is directed along the angular velocity, and it is given by I omega for a body which is under rotation. Now let's look at principle of conservation of angular momentum. Very similar to principle of conservation of linear momentum. So principle of conservation of angular momentum says that if net external torque acting on a system is 0, then the total angular momentum of the system is conserved. Right? If there is no external torque acting on the system, then the total angular momentum of the system is conserved. So whatever happens, like whatever changes go inside the system, they cannot change the angular momentum of the system. Now we use this principle in a lot of places. Like one of the places which is very common is where a girl in a skating ring wants to spin. Now what does she do? She spreads her hands and then gives a kicks herself to rotate, and then she brings her hands closer to the body. Now when her hands are spread, what is happening is moment of inertia is high, and when she closes her hands or brings the hands closer to the body, the moment of inertia decreases. When the moment of inertia decreases, what happens? Angular velocity increases. You can see a figure which tries to explain a similar situation. A person lifting weights is having his arms spread like this. Because the arms are spread, the mass is away from the center, so moment of inertia is more, and he gives himself an angular velocity omega. Now what happens is after he gives himself an angular velocity omega on the chair, he brings the masses closer to the body. Now when he's bringing the masses closer to the body, moment of inertia is decreasing. As a result of that, angular velocity is increasing. So we can increase or decrease angular velocity by changing moment of inertia. One simple thing that happens with everybody, but we often don't realize is, if sometimes we slip accidentally, then what happens is we'll see that our arms automatically rise. Now why does this happen? When we slip, our arms rise to increase the moment of inertia. If the moment of inertia of the body is increased, what will happen? Then the angular velocity is decreased. That means the tilting effect will be decreased, and you can balance yourself easily. That is why what happens is when we slip, we unintentionally raise our hands to increase the moment of inertia. Now the questions that we generally get on conservation of angular momentum is they will give us a system where we have initial angular momentum and we are required to find final angular momentum. In this case, we have two bars of moment of inertia I1 and I2. Now initial and there is no external torque, and the upper disk is slowly placed on the lower disk. Now what is initial angular momentum? Initial angular momentum is, I can write I1 into omega naught. Because the upper disk is not moving, its angular momentum is 0. Now what is final angular momentum? Now both the disks are moving together. So I can say total moment of inertia is I1 plus I2 into omega. Omega is the final angular velocity. So if I want to find final angular velocity, what can I do? I can take I1 into omega naught equal to I1 plus I2 into omega, or I can say omega equal to how much? I1 into omega naught by I1 plus I2. In this way, if I know angular velocity before any change has taken place, then I can find what is the final angular velocity of the system. It's not necessary that always the body should be, combined in the final situation. It can be the other way around also. Initially, there is a system, there is a single body, and after some time the body divides into two bodies. Even that case, we can use the conservation of angular momentum principle. So that is what is there in angular momentum. So we have seen what is angular momentum. Then we have seen what is how do we find angular momentum of a body under linear motion. Under what condition angular momentum of a body under linear motion is 0. Then we moved on to angular momentum of rotating bodies, and finally conservation of angular momentum. We have seen that when net external torque acting on a system is 0, then the total angular momentum of the system is conserved. And finally, a few examples to understand conservation of angular momentum. Hope you could follow this. Thank you very much for watching this video, and keep watching Get My Classes. Thank you very much.